All right. Well, thank you for all of you to join us for the talk. And I'm Heinrich. I'm from the team Berlin United. We are participating in the Standard Platform League usually, but we have been participating in development of a humanoid robot and want to share our current state with you. And yes, so let me see. Oh, yeah. So our talk will consist of 3 parts. We have also 3 presenters. And my role will be just to give you a small general introduction into the project. And then the next parts will be taken over by people who are more knowledgeable of those parts than I am. So as I said, I will give you the presentation, and then Anastasia will give you more details about the Gretchen robot itself, about the parts and all this. And then Matthias, who is the originator and the guru of the hardware, he will give you more insights into this magic sensorimotor board he developed, which is used on Gretchen as well. All right, so yeah, let's start with a short introduction. First, let me introduce ourselves. So I'm Heinrich. We're all from Humboldt University, basically. I'm a scientist and I'm still a PhD student at the Humboldt University, and I'm leading the team Berlin United. Anastasia is working on Gretchen and as part of her bachelor thesis, and you see her in the middle assembling the robot here. And Matthias on the right, he is a PhD student and has been with us on and off for a very long time, and also participated in RoboCup a long time ago as member of our humanoid team. And so now, parallel to finishing his PhD, he is founding a company, Jetpack Cognition, which creates and builds cool stuff, cool robot stuff. All right. Well, so very brief to the motivation and to our team. Like, what's our perspective? Yeah, we are Team Berlin United. We have been with RoboCup for a very long time in different leagues and different configurations. So we mainly participate in SPL and full-length league back in the day. But yeah, I put it in the brackets. We also had a team in hardware in humanoid league, where Matthias is part of that. That's why I listed it here. And yeah, so our main focus is on the software. So we usually don't have enough resources to build robots ourselves. We have some knowledge, of course. We have a 3D printer and all this, and we like tinkering with boards. But we're all computer scientists, and we don't have a strong mechanical engineering background to actually build a robot, and also not enough resources. So the idea is, our motivation is to build a robot in a sustainable way, meaning partner up with other people who are very knowledgeable in building robots, and yeah, so cooperate with them, and that's what we are doing basically, right? So this robot is developed in a cooperation, and yeah, so at this moment we want to collect experience with the hardware, and yeah, so you see our website down there, and that's our team at the German Open. Yeah, so to give you that's probably the most boring slide you're going to see in this presentation, but I thought it would be maybe good to give you a small overview what I mean by sustainable. By sustainable, I mean that the robot should be not only used in RoboCup, but the idea is that, you know, the robot has also other potential uses beyond RoboCup, so it can basically carry itself, right? So, and the aim of Gretchen is to have a good robot which can be used for education, which means it should be accessible by students who are not that experienced, that there is a teaching material and good documentation, and it should be very affordable, so it cannot be too expensive. But then on the other hand, if it needs to be used for research, it would be good to use it for research. It needs to be complex enough, extensible, right? So you can actually make complex experiments and have access on different levels, right? And yeah, so we just heard in the last talk, it should be robust to participate in RoboCup, and that's also one of our aims. So one day, perhaps, you know, Gretchen will reach the stage where we could use it potentially in RoboCup. And yeah, but right now it's in the prototype phase. Okay, so now our approach is, you see on the right side, we try to
Heinrich,
yeah.
I'm sorry. Part of the slides are cloaked by some windows or something. I think the audience cannot read. Yeah, this exactly. Can you?
No, well, that's Zoom.
Ah.
Crazy stuff. Thank you for letting me know. Okay.
Yeah.
Now it's better, no?
Yeah, it's very good. Yes.
Jesus. Okay. Wow. Technology, huh? Okay. Yeah. So we try to keep the robot very modular. So there are not too many different components that we have to maintain, and then of course open source and open hardware, and for as many components as possible, because we researched open platforms developed by other teams and many groups, which are really great, but still some of the core components are proprietary. So the hope was, you know, to make us as much as possible open. And yeah, accessible manufacturing methods, right? So something which can be used actually by the students. So nothing too fancy. And yeah, we hope also to learn from other platforms. So we're looking around and looking for collaborations. On the next slide, I will just briefly show also who is involved in the project. So if you're you know, interested, or if you see like, oh, we have a better solution for this or that component, so just reach out to us, and yeah, so we will be happy to find connection to the humanoid league community here, and to build bridges here. Yeah, in the current state, the robot is in the prototype stage. There is, of course, everything is open source and open platform, so everything is published online so far, and but there is also an assembly kit, which can be, I don't think it is sold yet, but like the idea is to have an assembly kit, which make with some of pre-built parts, so it's easier for to build up the robots if you don't have experience in developing humanoid robots yourself. There is already a documentation which is quite extensive. There is a link. And we already use it in yeah, seminars. So for now, for teaching. Then this is going to be the last slide of the presentation, just to give you an overview of who is involved in this project. So Matthias has been working mainly on building various electronic components and developing parts and so on, also for other robots. And then at some point he joined AI-Brain, and they developed a platform Gretchen, and the development at AI-Brain continues. So they have a development team working there on this. So they contribute from that part to the robot, and so we are as a SPL RoboCup team, right? We contribute our experience from RoboCup software testing, and also use the platform in teaching. And yeah, so far from our team was not like, say, heavy development. So we are you know, the software people, so on. And Matthias, of course, continues to develop work on the parts, and you will see more details in his presentation then. Okay, so I hope it gave you a small overview over how the Gretchen project is structured. And then I would hand over to Anastasia at this point.
Okay, yeah, hello, can you hear me?
Yes, we can hear you.
Okay, great. So hello everyone. So as Heinrich mentioned before, I'm Anastasia. I am a computer science student at Humboldt University, and I've been working with the robot Gretchen as a part of my bachelor thesis. And I'm excited to present you the structure of the robot together with some assembly details. So let's move on to the next slide. So, and as mentioned before, the goal of the robot Gretchen was to provide a low level and a low cost access to bipedal robots, for software and hardware. All of these sketches, the assembly documentation, and the code can be found on this on the following Gretchen repository in GitHub. On this image, you can see a prototype of the Gretchen robot. It's 74 centimeters high, weighs around 5 kilograms, and is powered by 10 servo motors, so it has 10 degrees of freedom. You can also see the main materials which were used for manufacturing it. These are the yellow wooden parts, as well as 3D printed components such as the joints and the feet, as you can see. And then it has also some drive parts like the bearings and the tooth belts and various electronic components. The overall price of the materials lies at around 1,400 euros, so it's a low-cost robot. And yeah, I'm going to elaborate more on each of these hardware components in the next slides. So let's move on to the wooden parts. So here you can see that how the wooden parts look like. So the thighs, the shanks, and the lower torso of Gretchen are made of plywood. We used a half centimeter thick plywood plates for Gretchen because the laser cutting machine, which was used for cutting them, could cut only through half centimeter thick wooden surfaces. So then these surfaces had to be glued together. You can see in the picture above how the glue was drying. And after this was done, we had to color them and to coat them in order to protect the surface. So yeah, let's move on to the bearings, which would be the next assembly step. So the bearings are ensuring a smooth connection between the joints and the wooden body parts. They should be connected on both sides of the wooden plates. So as you can see in the second picture, so in the middle picture. And as the reason why exactly these bearings were chosen is because they are self-centered, meaning that they fit into the holes of different sizes and are working well, especially for uneven holes. And this is mostly the case like in handmade components. And yeah, so you can see the bearings on these two pictures marked within red circles. Yeah, let's move into the next moving component, which are the tooth belts. So these tooth belts are flexible bands which have carved teeth into their inner surface, as you can see in the picture to the left, and they are designed to run over matching toothed pulleys. So on the other two pictures, you can see the motor and the other pulleys and the tooth belts around them. So these belts ensure an indirect transmission between the motors and the joints, and thereby make the connection between them more elastic and protecting the motors from direct damage and heavy loads. Yeah, let's move on to the 3D printed components. So Gretchen has the following 3D print components. These are the joints, such as the hips, the knees, and the ankles, the feet, and I'll talk a bit later about the pulleys and the motor covers. So as you can see in the pictures, so the hip joint on the top has 2 degrees of freedom each. It has the pitch and the roll due to this inner XY integrated pulley, which you can see on the left side of the picture above. Then the knee joint has 1 degree of freedom on each foot, so this is the pitch. And again, you can see this on the picture, the right picture below. The outer side of the knee has, again, this pulley, which will be then connected to the motor via the belts. And the ankles, which are on the left picture, have 2 degrees of freedom, the pitch and the roll, which are ensured by this cardan joint mechanism. You can see it on in this frame of the foot inside. Yeah, and another interesting thing about the feet is that there's no right or left foot. Both feet are perfectly identical pieces. So let's move on to, as for me, the most exciting part of Gretchen. These are the servos and electronic components. So this is the overview of all the of the main electronic components. So you can see above the 10 servo motors, which are used for powering Gretchen. And then on the left picture, you see 10 custom boards, which were designed by Matthias and his team while creating Gretchen. Then some electronic components, which will be then soldered to these boards, and some self-made cables. These are the bias cables, which will then connect the motors between themselves. Yeah, so let's start with the servos. We used the following high-tech servo, the HS805MG. It has all the basic components which normal DC servos have. So it's a brushed DC motor, a gear train, a potentiometer, an integrated circuit with a microcontroller. Its stall torque is 2.4 Newton meters. It weighs around 200 grams, and it is pretty big. Yeah, the price lies at roughly 50 euros, depending on where you buy it. So the thing is, these servos cannot be used as they are for powering Gretchen, because they cannot be connected to other servos directly. And also the firmware of the microcontroller cannot be easily changed. So we couldn't even find a data sheet for that microcontroller. So therefore, Matthias and his colleagues designed the Sensorimotor custom boards, which would extend this low-cost servo with additional features. And let's see how this custom board looks like. So these boards are, so this is how they look like. They're completely open source. Everything, like all the sketches and the circuits, you can find them on this GitHub repository. So an interesting thing about them, these boards were not specifically designed for this kind of servos. They would work with any servo motor which works in a range of 6 to 12 volts, and yeah, for any DC servo, of course. So they have an easily programmable microcontroller, an Atmega, which is also met in many Arduinos. It works on a higher voltage range than the old servo than the old board from this servo. So it can work with a voltage up to 12 volts, and therefore it can generate higher torque at this kind of voltage. As you can see in the picture above, there are some electronic components. So there's a capacitor, an ISP header, temperature sensor, an I2C connector, and 2 white bus sockets. So all of these components will be soldered to the board before using it for our servo. And yeah, so these 2 white sockets, they are for the RS485 bus. So therefore we will be able to connect the servos easily between each other with a simple cable. And also these boards are capable of more sensory measurements than the default board of this servo, such as the current, the temperature, the position, the voltage, and also we can get external measurements via the I2C bus. So let's move on and see how we change, how they insert this servo into this board into our servo. So of course, the first logic step is removing the old board. You can see the picture above to the right. So there's like a gathering of the old servos, the green ones, and then the new ones. And in the background, you can see the opened servo boxes. Yeah, and another thing to note is that we keep the potentiometer wires. So you can see them on the picture to the left. These are these colorful yellow, red, and green wires. So the idea, of course, behind it is that we want to reuse as much from this servo as possible. We don't remove everything. So yeah, then the next step would be preparing these wires for soldering them to the board, as well as prepare extra wires for the motor, because the old board of the servo motor was soldered directly to the DC motor. However, now we will have 3 wires connecting the board to the motor. Yeah, after that is done, the next step would be using the 3D printed covers to insert the board inside them, because yeah, now that we have a bigger board, it will not fit into the old servo cover. Yeah, so these are 2 new 3D printed components, which are like add-ons to our modified servo. Yeah, so once we made that, we then close the motor cover, and on the other side, we mount the 3D printed pulleys to the motor. And yeah, in this way, our servo is done. However, this step was one of the most challenging ones. And on the next slide, you can see 2 of the main challenges we had. So the first one was that while desoldering the old board from the servo motor, I accidentally removed most of the motor pins, which made it almost impossible to solder anything to the motor. So you can see the picture above. There's this, so on the surface of the motor, we can see a very big soldering soldering place where we had to somehow find a way to solder this this wire to the motor. So this wasn't possible with a simple soldering iron, at least not with ours. So we had to use a gas torch, which is able to deliver more heat and also a lot of soldering fat. And and then we somehow managed to do this. So this was pretty adventurous. And another challenge was that the 3D printers sometimes have a small error. It can be maybe even 1 millimeter. However, for this kind of small pieces, this means a lot. So in the case of the motor covers, this hole on the side where we have the bus cables and going in, the hole was a bit and we could insert the board inside the cover. So what we did, we used a drill in order to drill the hole, make it wider, and then it worked. All right, so let's move on to the next step, which is confectioning the bus cables. So self-made cables are another important component which keeps the overall cost of the robot lower. So we confectioned 9 cables. Each of them had 3 black and 1 red wire. They were then twisted pairwise in order to reduce the noise. And we used silicone wires, which are very flexible and very heat resistant, which made the work with them much easier. So here you can see the process on this pictures, how we confectioned each of these cables. All right, and now we're close to the final assembly steps. So this is basically putting everything together. We first mount the motors inside the pre-cut holes of the wooden plates. Then we had to screw the motors in. The next step would be then mounting the tooth belts, which is also an interesting step because they have to be put in a certain position of the motor, of the motor's rotation. So Matthias made a great video, which he also posted on YouTube, on how to make it, so that it's easier for us to just follow his steps. And after these tooth belts are mounted, the last step is connecting everything, like the bus cables, and tightening them. So on the picture to the right, you can still see the cables being loose and being all over the place. So that's not really what we want. So that's why it's important to tighten them so that the cables don't get damaged when the robot starts moving. Yeah, and the last hardware slide is about the shells. So the 3D printed shells were designed for the legs and for the hips, in order to protect the motors, the cables, and the belts, of course, from any collisions and so on. So that's so you can see how Gretchen looks like with the shells. It looks more appealing, and they were made in they were 3D printed in an Ultimaker printer. The material was tough PLA. They're very lightweight, however, they're also quite robust. So you can see on the scales, like on the left picture, someone pushing this these shells against the scales with around 10 kilograms, if I'm not mistaken. So they're pretty robust. Yeah, and they're also very easy to unmount and mount. You can see in the picture in the middle below, like there are like some clickers, so it's very easy to like click them in and then unmount. So yeah, very handy. All right, so now I'd like to give you a quick overview of the communication between the servos and the PC. So the first way of communicating with them is flashing the firmware, which is the most important step, because without the firmware, our boards will not be able to communicate with the computer. And we use for this the ISP header, which we previously soldered on this board. And flashing the firmware can be done in many ways. We can use an Arduino, as Matthias did, and which is also written in the assembly documentation. However, we used with Heinrich the USB to ISP programmer, and yeah, this worked out just fine. And then once the firmware is flashed, we can finally connect to the bus and start to move the robot. So you can see on the right side, like this RS-485 bus, which where the motors are connected between each other, and we can connect the computer to this bus via a USB to serial bridge. So right now the connected point is at the foot of Gretchen. Maybe we will have time to show it later. So yeah, we connect this serial bridge inside the foot of the Gretchen, and then with a USB connector to a PC. And another important thing is, of course, the power supply. The robot needs power in order to move the motors. So we used this little 7-volt battery, and it worked out just well for powering, for making some short tests. And yeah, we also soldered this this USB to serial bridge together with this battery. However, I'm sure there will be a better way of doing it in the future, so that it's more robust and that the robot can also move a little bit further, because right now it's more of standing on the same place. All right, so the next slide gives you an overview of the software architecture. Here on the left side, you can see the robot with the RS-485 bus and the firmware, which is running on each of the boards of each motor. And then you can see that the USB to serial adapter goes to the foot of Gretchen and then to the PC. And the PC should be a Linux machine. So far, the code can be only compiled on Linux. And we have basically two main modules. We have the C++ library, which is a low-level module, and we have the Python API, which is a high-level one. So the low-level one is the C++. It ensures all the basic communication, the serial communication interfaces. The PID controller also runs there. So yeah, so right now we have this loop between the motors and the computer, that at each time step the motors have to send their position to the computer, and then the PID controller will calculate the next position and send it back. So there's a little delay. However, we are planning to move the PID controller on each of the boards in the future. Yeah, so that's what the C++ library does, and the Python API is basically making it much easier for us to program new movements of the robot Gretchen. It is yeah, very basic. It has Matthias wrote a few nice examples on how to control single motors, and it makes it much easier to start programming the robot Gretchen without having to understand the complex C++ libraries. And yeah, next I would like to show you a few videos of the robot Gretchen moving. And yes, and I will then pass the word to Matthias.
So, and here you can see some example of Gretchen making couple first steps.
really noisy, so we'll wait a moment.
So I disabled the sound now.
Okay, this were actually the first steps where you put just a basic oscillator with some phase delays on this to simulate a walking. So it's not actually a walking; it's more just a functional test. So yeah, thanks for having me here. After this short introduction video here, how Gretchen is look like in real life and performance, I will go over to give you some details on the Sensorimotor, which is the motor control board, which is like kind of the spinal cord of the Gretchen, and it was maybe Heinrich, if you thank you. It was initially meant as a open source and low cost replacement for dynamics servos, because we use them all the time in the past when we build robots, and we often find us in situations where okay, the dynamics motors were too expensive, and especially when I was out of academia for a while and wanted to build a 4-legged robot for my personal project on my own. I was in a situation that, okay, I cannot afford 4,000 euros for just the motors or something. So I decided to go another way here, and then looked some project and found the Open Servo project and others. And so I kind of created a control board for having smart servo capabilities on a low cost and open source basis. So this board is actually meant to be motor brand agnostic, so you can use it with any kind of servo within the power range. Yeah, so you don't want to make specific servo here, because they change all the time. The prices change, and the material what they use and stuff. So you can switch over and can keep all your software and all your firmware, keep it stable, but just change the hardware underneath. So, and it's self-assembly, so it's to reduce cost even more. And you can hack the firmware when you're not when the current firmware is not sufficient for your needs. You can just override it and make your own one. It's based on an as Anastasia already said, on an 80 mega processor, which is very similar to from the board layout, very similar to the Arduino. If you're kind of familiar with the hardware, you will easily find your way to the datasheet and stuff. There is Heinrich. Can you show the next slides, please?
Yeah, just let me know when you want to switch, and then I will just...
If you can make the next slide, please. Yep. So one thing which is special is that, like in the dynamics, you can connect several motors via a robust bus. It's RS-485, so you can, let's say, connect up to 20 or more motors without problems, and technically it's more than 100, but you have to think of some other constraints, like how much data you want to transmit, etc. But technically you can connect several hundreds of these motors. And yeah, my initial motivation for this was just for my 4-legged robot. So I needed 12 of them, and I already split the bus a little bit, so to have more a tree-like architecture, not a single line. So you can connect several of those motors in a single line bus. I will go on the next slides. You can see a picture of this. If you can skip, please. Yeah. There you see some boards connected without the motors, and you assemble. And this is actually the 12 motors. The PCBs are yellow here. This was the first version. The black ones as the current version. On the next slide, there will be some technical details. It's a block diagram here, where you can see the processor in the middle, the ATmega 328P. It's the same on the Arduino Nano and Arduino Uno, I think. On the board, there is an integrated H bridge where all the MOSFETs, power transistors, are integrated in one single chip. So it's very handy also for soldering and for prototyping. And you can attach a lot of different motors to this one. You have a bus driver, an RS485 bus driver, which is fault, which is robust against connection faults. So if some cables are broken or something, then usually nothing happens to the bus connector. It's very robust against electrical faults. And yeah, and the board collects a lot of sensory data like the temperature, position, battery voltage, motor current, etc. And all these data is reported over the bus. If you send a request to the motor, then you get all the sensory data from each motor. And another, it's a tiny feature, but it's very handy, especially if you think about that everything is assembled by yourself. There's a reverse polarity protection included, which is not very common in low-cost hardware, because if you for some reason swap the cables or have a broken cable, then you don't want to lose your hardware. So it's protected against wrong polarity. So on the next slide, you can see just the board layout and where to connect all the cables. And you see that there is a I2C connector on the left, where you can extend the board with some local sensors. Let's say you have a handy magnetic encoder also available and want to have a more high resolution position sensor or whatever. You can connect it via I2C. Of course, you have to write some firmware for it, but the board is capable. And since I2C is itself a bus, you can also connect several sensors if you like. Yeah? There's also a debugging connector below, which is just the FTDI RxTX UART standard. And it's a common flasher device. It can all common ABR flasher devices can be used. So I think pretty much of the hardware guys of you already have something in your shelf, so you can start right. Otherwise, you have to rewire an Arduino and can also use it for flashing the device. On the next slide, yeah, you see all the motors connected in the bus here for testing. The bus is, some details on this is, if you have already used a differential bus, then you know that there's actually only a single wire, a single signal transported on two wires, and it is inverted in phase in polarity, so that the transceivers can subtract the original signal from the wires, and so the noise is actively cancelled out here. So it's a noise rejection mechanism for this. The cables need to be very close to each other, the data lines, and for this you usually make a twisted pair of them. And if you need longer cables, then you need to reduce the reflections with resistors at the very ends of the transportation line, so to enhance the signal quality. But actually, you can use these motors for different projects too. So you can make cables which are 1 kilometer or something. Yeah? So it's a very robust and very nice bus system here. Pretty old, but it's also similar to CAN bus, but without the protocol overhead here. And there's just a custom protocol and here is an example of the motor request, which you send to the motor, and it's just 6 bytes, and then the motor will respond with the sensory data. Oh. And this motor request also sets the new set points for the motor control voltage. On the next slide, there's just some details on the H-bridge which is used. As I said, it's an integrated H-bridge, so all the 4 power transistors which you see on the right side are integrated in one housing, including the flyback diodes and stuff. So with the interface from the microcontroller, you actually control not every single transistor, because this could lead to shortcuts if you do it accidentally wrong. So this is covered by the logic, and you set a PWM signal and a direction signal, and the H-bridge will care of everything which is concerned with the transistors. It is up to 6 amperes. This is of course a peak value. So if you apply let's say for the stand-up motion you saw in the video before, if you do it too slowly, then the H-bridges will automatically shut down when they're going too hot. So for this, we usually use some kind of heat sinks on the chips for the motors which are under heavy load. The H-bridge has a SPI interface, so it's very handy for diagnostic data controlled by the microcontroller. I must say this is not yet implemented in this firmware, but it can be. So and a nice feature is the freewheeling mode, which is very nice if you want to make relaxed movements of the limbs. On the firmware, some words on the firmware. On the next slide, there is just the internal 1 kilohertz loop, so everything is a little bit faster there, but communication is at 100 hertz. Usually when you have 10 boards or something, if you wanted to have it faster, then you can do this. The board will respond instantly when you send them a package. So you can, if you have only 2 boards or something, then you can go up to 500 hertz or whatever. It's written in C++, and we use the XPCC framework. Please have a look at it. It's now called Modem. It's a very nice framework for modern embedded programming. If you want to don't want to have everything written in C, then please check out this one. The guys are very great. It has a sconce build system, and the firmware currently only supports the PWM mode. And next, as Anastasia said, we want to integrate the position control, PID controllers, etc., directly into the firmware. But this is some work to do. Some details on the LibSensorimotor on the next slide. This is just the C++ and Python wrapper then for controlling the motors from your PC or Raspberry Pi or something. So I used it in different architectures, and even a Pi 0 is no problem for supporting up to 10 or 15 sensory motors. So and the control modes are currently in the library, and they, as I said, they will move into the firmware directly. And there's currently an embedded library for STM32s, which is under development, and I will probably can release it this year. On the next slide, there are some other projects using Sensorimotor. On the right hand side, there's Hannah. This is my PhD project, which is a 4-legged robot which has 12 sensory motors built in. And since 4-legged is a kind of different topology to connect the cables in a single line, so I decided to make it more a tree-like structure, and also added some control boards in between. I call them limb controller. They're shown in the middle, and these limb controllers are each connected to 3 sensory motors for each leg. So and each limb controller is then connected in a separate bus. But this is all more or less the same topology as you have heard before here. It's all RS485 and custom protocols and stuff. And on the left, there's a testing robot, which is called FlatCat. It's just 2 degrees of freedom. And if Heinrich could, yes, thank you. This is only very small testing robots, which is also running with 2 Sensorimotor boards. And here I use a more modern control loop, which is just based on position data, and it estimates the force which is applied to it and can race against gravity. And if I push it, then it's kind of withstanding the force in a very handy way. And so just to show an example, which is for the motors. Okay, and on the last slide, I will give you some outlook on current and future developments. There's the next hardware revision is coming soon, which is easier to solder and a little bit smaller. And the temperature sensor, which was kind of hard to solder below the motor, will now be integrated and will be pre-assembled as an SMT part directly on the board, and will make everything more robust. So the LibSensorimotor will be released as an embedded version for Arduino and STM32, and there are currently 3 spin-offs of the Sensorimotor boards, which go in different directions, but every one of these will speak more or less the same protocol. So it is kind of a growing ecosystem here. So is this a node? It's called the node, which is an Arduino-based daughter board. So you can put your Arduino Nano on it and control a lot of servo motors and sensors, potentiometers, or capacitive touch sensors, MPU, and all are connected via the same bus, so that you can have different components in your robots too, like other sensors and stuff. And there is a Kiwi, which is a micro servo version. This will be a very reduced version of the Sensorimotor with only everything which needed, because the space requirements in the micro servo is so hard. And there will be a cargo version, which is probably the most complicated stuff here, because it is a brushless variant, and you have to special care for the high power board layout. So this will take a while, but stay tuned. We provide this. I will provide information on our Jetpack homepage. So as Heinrich said, I'm currently creating a little company with all this robot stuff, and yeah, we'll hope to provide the community with cool robot technology directly made from maker philosophy and open source and stuff. So yeah, thanks for listening. Please put your questions in the chat or whatever.
Yes, so thank you, Matthias. Thank you, Anastasia. And yeah, so here's just a little overview over perhaps what you've just seen. And if you have any questions, so feel free to. There is a raised hand. So Humayan, please.
Humayan?
Yeah, do I have something to do to?
No, everyone can unmute themselves.
Hi, Matthias. Thank you for your talk. Yeah, it was really good. Just wondering about the communication speed. You said it's currently at 100 Hertz. Mm-hmm. Is there a limiting factor that like, can it be increased as well, or do you think?
Yeah, the current limiting factor is the 80 mega 328, which has 1 megabaud UART speed. So let's say, yeah, I think there's a possibility to increase this on 2 megabauds with some tricks, and if you reduce the package size, and so if you let's say tweak a little bit the firmware and reduce it to the minimum communication needed, then you can increase it, of course. So, and if you let's say have for example, on the HANA robot, there are only 3 boards per leg in a single bus, yeah, because there's a separate controller, and here I can increase the communication speed to 300 hertz or something without problem, without changing anything. So, and when you change something, you can easily make it to 500 hertz or something.
Cool, sounds good. Do you think that like? Did you also look into a separate microcontroller, or you think
Yes.
at 80 mega would? Okay.
Yeah, it was just a pragmatic decision back then, just to take a working circuit which was already tested, and things need to go fast. So
yeah.
And currently on this limb controller board, which I showed in the middle, maybe Heinrich can skip back to 2 slides or something. There is already an STM32, and this one already has, yeah, here in the middle. This has 3 to 6 megabauds or something. And more power. So maybe in upcoming versions we will integrate this processor on the board. One requirement was for me to have it hand solderable, even if it's SMT parts. If you choose this 80 mega, then you can with some practice you can solder it by hand. You don't need pick and place machines. If you choose to take an STM32, then it's very unlikely that you can solder it by hand without special equipment like a stereo microscope or something. So you will probably struggle a lot with the fine pitch 48 pin housings. So that was the decision of the 80 mega. Yeah.
Cool. Awesome. Yeah. Thanks a lot. Yeah. It's pretty good work. Thanks.
There is another raised hand by Jasper.
Yeah, hi. About the point you made earlier about the microcontroller, we have been using the ESP32 for a while now, and it's pretty fast and has 2 cores, so we just use one for communication and one for all the working stuff, basically. So it's also really easy to solder. It's a bit bigger, maybe if you want to look into that. But my actual question is, Anastasia mentioned that you use silicon wires, and as far as I know, they are a lot less abrasion resistant than like normal PVC wires. Have you had any problems with like cables breaking, or like I'm just looking for your experiences with this material, because we've always used different kind of wires, like different kind of isolation.
May I, Anastasia, or will you?
Yeah, sure.
Okay. We use this cable also in the lab before, since, let's say, since 2008 or something, and I honestly will never need another cable. So I can give you the order number. It's I think you can order it by Conrad or something. It's great. It's temperature stable, so you can easily solder and stuff without burning insulation, without melting insulation, and it's so flexible that you can put it everywhere. So of course, if you need a cable which is, let's say, directly exposed to wear, then you probably need something else. But it's pretty good. So it is superior to the original Dynamics cable. Yeah, if you used this before, then this one is very good here. It's a very thick insulation, actually.
Okay, could you just send me the Conrad order number maybe on the chat or something?
I'll look it up and put it in the chat here.
Thank you.
Maybe I can add a small thing here. Matthias, as I remember, like these cables were also used by your team when you participated in RoboCup. So they're sort of RoboCup tested. I don't know. Maybe you can comment. Did you have any cable breakings during RoboCups back then?
I mean, when there were cable breaking, then this was due to bad cable guiding, right? So we all design our robots ourselves. So it is usually the last step. Then you say, okay, where should we actually put the cable? And then you think of this a little too late, and the cable is kind of, let's say, under stress during normal motion of the robot, and then you of course have some breakage, but if you do not expose it to the mechanical stress directly, just normal bending and stuff is and heat and temperature, UV lightning, etc. So it's very stable. So that's my experience with this cable. Let me show, where is it?
Maybe also about the, I don't know, basically another question. Have you thought about maybe using the stuff that Dynamixel did with the X motor so that you can guide the wires out of the axis of the motor, basically? So what they do is that on the side where the motor is not actuating, where basically a flywheel is, in the middle the cable comes out, so basically it never has to move in the robot.
Yeah, I recently saw this. This is very nice. So yeah, no designs I did no designs in this direction, but yeah, it's Dynamixel motors were always an inspiration. So as I said, we use them very heavily. So yeah, it's good.
Okay, so Ludovic is raising his green check mark as he can't raise his hand.
Yes, exactly. Well, I had a question about the connectors from the RS 585, because that's one of the problem we had with ohmic loss when you have a little bit of current, that you tend to lose 1 or 2 volts at the end of the tree. Yeah. So have you considered using other connectors, or is it just used by default because Dynamixel is using it?
So I think they are specified for 3 or more amps continuously. So so I actually did not recognize voltage drops in about 1 volt range. So how many motors did you connect there? So that is 1 volt is pretty much.
It's for the legs of a humanoid robot. So it was, I think, 6. And between the first and the last, we had even like more than 2 volts when the robot was standing up or kicking for highly dynamical motion. Yeah. So during peak of current. Of course.
Yeah, okay.
But it makes control way harder and simulation gap with reality even higher. So that's one of the very difficult part due to electronics.
Yeah, maybe you could increase some local capacitance or something for buffering. Maybe the bulk capacitance on is not sufficient here for the load you apply. I'm not sure.
Maybe that's also one of the reasons I saw is that you have a big capacitor on your board.
Yeah, we currently use 220 microfarads something, but it can be go up. So the connector is pretty big here. So you find easily on Reichelt or DigiKey, find easily capacitors which go up to 1000 microfarads or something.
Yeah, I don't have the internal design of the dynamic cell in mind, but maybe their capacitors are way lower, and that's why you see this problem that much.
I'm not sure. So, but yeah.
I mean, maybe to add here just a little bit is that we didn't try, strong kicks with these robots yet. I don't know, Matthias, if you performed any very stressful tests yet. I mean, so far all the tests were quite gentle, so maybe this kind of problems will show up eventually, but not so far.
Yeah, there were some more heavy load tests on the HANA robot, but there's so I mean, usually if you start with the stable power supply like lithium polymer batteries or something, then you can pretty much exclude the power supply because they can deliver up to 60 amps or something. So then should be some problem with the cable probably. I don't know. I'll put the, 1 second, the link for the cables. Okay, any more questions?
There was a question in the chat during the presentation. I'm not sure if it has been answered explicitly about the accuracy of motor angular positioning.
So the accuracy of the PID must be tuned by yourself. So there's every PID parameter accessible for your tuning because it is, since the Sensorimotor board is agnostic to the motor being used, so you cannot make predefined parameters here. So you have to find out yourself, and the accuracy of the sensor is 10 bits, so it's not that much of a precision. But the Sensorimotor board was originally built for a 4-legged robot for dynamic motions, let's say, where precision of the positioning is not such important, I think, especially from my control philosophy point of view. If you need higher resolution, then you should consider to add a magnetic position encoder to the I2C or something. Then you get more precision, and then you can more fine-tune the control loop. And also, as Anastasia said, the current version of the PID is sitting in the control library in the PC or Linux machine, so there's a delay. So this also restricts the tightness of the position control. And if it will be changed to be in the firmware, then it can run at the 1 kilohertz loop and will be pretty tight. So I put in the chat the link to the cables. It's unfortunately it's a German site, but maybe you can switch it to English.
So I don't see any raised hands anymore, and we are 5 minutes over time. So I don't know if there is a last question or so. Otherwise, maybe we continue the discussion in the Discord.